Welcome to Geek Fun Facts Online. Today, Peacener, we're diving deep, not just into the water, but into time itself. Imagine, beneath the crushing pressure and silent darkness of the world's oceans, there lies a library. A library that holds the complete history of Earth's climate, stretching back millions of years. The books are layers of sediment, mud and ooze, stacked one on top of the other. And the text? That's written in the language of trillions upon trillions of microscopic fossils. These tiny relics are the keys to understanding our planet's dramatic past, and they hold urgent lessons for our future. So what exactly are these microscopic storytellers? They're called microfossils, the fossilized remains of organisms so small you need a microscope to see them. Think of single-celled organisms like foraminifera, which build tiny, intricate shells out of calcium carbonate. Or coccolithophores, algae that cover themselves in tiny plates that look like microscopic hubcaps. Then you have radiolarians and diatoms, which construct beautiful, glassy skeletons out of silica. As these creatures live and die, their tiny shells and skeletons rain down onto the ocean floor. Year after year, century after century, they get buried, layer by layer, creating a perfect chronological record. The oldest layers are at the bottom, the youngest at the top, just like pages in a history book. To read this book, scientists embark on incredible expeditions. On specialized research vessels, part of projects like the International Ocean Discovery Program, they drill deep into the seabed. They pull up long cylinders of sediment called cores, which can be hundreds of meters long, representing millions of years of accumulated history. Back in the lab, these cores are carefully split open, and the real detective work begins. Scientists wash the mud through fine sieves, isolating the countless microfossils. Under powerful microscopes, they begin to read the language of the deep. But how can a tiny shell tell you about the climate millions of years ago? Scientists use what they call proxies, indirect clues that stand in for direct measurements. The first clue is simply identifying who is there. Just like certain plants only grow in certain climates, different species of microfossils thrive in specific ocean conditions. A layer of sediment packed with species that love warm water tells you the ocean surface at that time was toasty. If the next layer up shows a sudden switch to cold-loving species, you know a major climate shift occurred. But the real magic is locked inside the shells themselves. As an organism like a foraminifera builds its calcium carbonate shell, it traps chemical clues from the seawater around it. The most powerful of these is the ratio of two types of oxygen, the common, lighter isotope oxygen-16 and the rarer, heavier oxygen-18. When the planet gets colder and huge ice sheets grow on the continents, they trap vast amounts of water. But because lighter oxygen-16 evaporates more easily, the ice sheets become full of it. This leaves the oceans with a higher concentration of the heavier oxygen-18, so a foram shell from an ice age will have more heavy oxygen. This single measurement tells scientists about both the temperature and the total amount of ice on Earth at that time. Other chemical clues, like the ratio of magnesium to calcium in a shell, act as a more direct thermometer, giving us another way to check the temperature of ancient oceans. By analyzing these tiny shells, layer by layer, up through a sediment core, scientists have completely revolutionized our understanding of Earth's climate. They discovered the cyclical rhythm of the ice ages, confirming they are driven by predictable wobbles in Earth's orbit, known as Milankovitch cycles. They found evidence of hothouse periods in the deep past, like during the Eocene epoch, when the planet had almost no ice and CO2 levels were sky-high. Crucially, these records have shown that Earth's climate doesn't always change gradually. It can shift abruptly, sometimes in the span of just a few decades. One of the most studied of these events is the Paleocene-Eocene thermal maximum, or PETM, which happened about 56 million years ago. A massive burst of carbon entered the atmosphere, causing rapid global warming and ocean acidification. The evidence is right there, in the microfossil record, showing a dramatic die-off and changes in species. The PETM serves as a stark warning from the past about what can happen when the carbon cycle is thrown out of balance. So why is peering into the ancient past so important for us right now? First, it provides context. We can see the range of natural climate variability, and it shows us that the speed and scale of the warming we're causing today is truly unprecedented. Second, it allows us to road test our climate models. If a computer model can accurately simulate the climate of the last ice age, or the warm Eocene, we gain confidence in its ability to predict our future climate. These ancient records help us understand just how sensitive our planet is to greenhouse gases, and that knowledge is vital for informing the critical policy decisions we face today. The work is far from over. Scientists are constantly refining these techniques and drilling for higher resolution records to understand rapid changes even better. But the story so far is crystal clear. These microscopic shells, buried for millennia in the cold, dark mud of the ocean floor, are not silent. They are eloquent witnesses to our planet's turbulent history. They tell a story of ice sheets advancing and retreating, of oceans warming and cooling, and of the profound link between carbon dioxide and the planet's temperature. They are tiny storytellers with an epic tale, offering us the wisdom of the ages to help us navigate the challenges of our future.